Hi, hello. Welcome to week 6. Now, can you hear me all right? Like this microphone always sounds a bit different here. Okay, cool. So before starting this actual lecture, let me take a step back and recap very briefly what we have done so far. In the very first lectures, we have introduced the basics of economics for option pricing, like where key concepts for replicating and arbitrage to calculate fair option prices. And subsequently, we've also developed techniques like Ito's lemma, Ito's formula, and so forth. But subsequently, we have seen two models for option pricing. The one last week was the Black-Scholes model. We have seen Black-Scholes PDE. That was the Black-Scholes PDE. And we've established many, actually, three numerical methods: forward, backward, the mixture of those. So that would be probably in the next slide. And this algorithm, if you run it, is an approximation up to this discretization error of your option price in this Black-Scholes framework. Now, that's fine. Like everything that I told you last week is valid. The only downside to this approach is up to the small errors occurring by our modeling simplifications, is that this numerical scheme is inherently low dimensional. So that means like solving these PDEs, and this will become clearer in the later parts of this talk, solving the PDE using the numerical method works very well in dimension 1 as we have done it, one-dimensional stock. Maybe two-dimensional stock, you can put up modifications of this approach that still perform well numerically. But as soon as you have an option that depends on multiple factors, think of an option that not only is a call option on Apple or only on Microsoft, but something that depends on a basket of options, 10 stocks, then all of these methods have no chance of giving you, like, converging, essentially. This will become clear later on in this talk. And so what we're going to do today is, actually, today, most of today's lecture will have nothing to do with math finance or quant finance. I will introduce to you the Monte Carlo method. So just hands up, who has seen or heard of Monte Carlo methods? Okay, maybe a third. Then for a third, it will be a boring lecture. For 2/3, it will be a hopefully very interesting lecture. So the idea about I will just quickly explain how this relates to the basis or the goals of our course. And to that end, we need to go back to week 3, actually, where I've introduced the simplest possible model that you can think of, a binomial model. This was the price and cash account today. That's in a year, so it can either jump up or down. That's it. The simplest model. And what we've done in this model, so V was the payoff at terminal time, and we're interested in the price of that payoff. And what we've done using purely like replication arguments is we've calculated the price. So that was the outcome of our analysis. To remind you, so V0 is the price of the option V on the stock in this one period model. And what I stressed back then, and I've written it there actually, is that V0, if you think about it, this P is a number between 0 and 1. Here you have P. Here you have 1 minus P. So what this turns out to be, discounted, but it's an expectation of a different, not the physical measure, which like it went up with probability 1/2 and probability down with probability 1/2, but are under a different, it's called risk neutral measure. But the crucial takeaway of this slide, and that's going to be the last sentence today about not almost the last sentence about finance, is that prices, or this price here is given as the expectation. So what Monte Carlo methods are about is solving or calculating or approximating expectations of various functions. And that's how it relates to this course, actually. And this is actually, this is a general phenomenon, and we will see that next week also in the Black-Scholes framework, that prices again are given by expectations, conditional expectations, under risk-neutral measure. So that was just to tell you how this lecture today places in the course. Okay, so what I will do is I will introduce the Monte Carlo method. And in order to do that, I will just also take a bit of time and recap again what is a random variable, what is its variance, and so forth, just the basics that we need to understand. Also the performance of the method, actually. I'll tell you a bit about the concepts behind, like that will be a central limit theorem, law of large numbers that underpin like the idea of Monte Carlo methods. That will probably be the first until the break, more or less. Yeah, I guess so. And after the break, I will tell you various methods that are central to Monte Carlo, like generating random data, how you generate random numbers, what are algorithms for that, what are variance reduction techniques, and so forth. Just that you have like a slightly more holistic picture that you will actually understand better what is going on. Okay, that's the program for today. Now, the idea of Monte Carlo methods is to use random numbers to approximate something which is actually not random at all. The expectation is just a number, right? And we're using random numbers to approximate this deterministic number. And so what turns out as a consequence, like this is very different to the algorithms that we've used so far. For instance, the Black-Scholes PDE solver, you have the algorithm, you have a discretization error, but you implement it in the computer, you click on run, you get a number, you click on run, the next time you get the same exact number, which is an approximation depending on how fine your grid is and so forth of the true value. But you get the same number. So a client calls you, asks what is the price of a call option with a whatever strike on Apple. You click run, you get the number. Different client calls you, you get the same number. Monte Carlo methods inherently are random. So you click run, you get a number. Next time you get a different number. And that obviously introduces some complexity. And for that reason, we need to understand very well like how random these values that we get are actually. Is it a tiny perturbation? Is it something completely different? So this is probably the part of the first part of the lecture. And as I said, like because of this downside, whenever you have access, the problem is low dimensional, it is simple, you can run your PDE methods or other deterministic methods, you would typically tend to do that in order not to worry about this problem. But still, like for complex problems where options are, say, complex, not necessarily smooth, high dimensional in particular, is where Monte Carlo methods shine. Yeah. And as such, maybe I should also say that, I mean, in all modern machine learning, like all of this is based on Monte Carlo methods. So there you have like billions and billions of parameters. The dimensions are crazy high. Everything, every large language model is run on Monte Carlo methods. Okay. So that's maybe also a point why this should be of interest, general interest to you. Cool. Now, let's start very basic. So remember, random variables are just, we will mostly deal with density. So we have density. Expectation is given by this form. You integrate density times identity. Variance is just the square minus the expectation square. And I told you last time, so I think we introduced this in the very first lecture I gave, week 2 probably, that the correct or the better way to think about this is as a measure of dispersion. So that's a neat formula, but that's sort of the true, that underlines the true meaning of variance, namely that you have expected value, and it measures how random this random variable really is. So in particular, if you have a random variable x, they can have the same mean. One looks like this, whereas one looks like, oops. Okay, that's a bad picture. But you get what I want to say. Like one, so here, in this one, the variance will be high. This one will have relatively modest variance. And the reason why this is really important for us is, remember, so the typical error that we expect is square root of the variance, standard deviation. So if we sample from this random variable, then that's the typical error. So in these methods that we will introduce, it's always important that the variance is very small. Okay. Right, yeah. And if you have a variable, then concatenation with like any function essentially is also a variable. That's the formula for the expectation. So f identity is exactly the previous slide, but in general, we're interested in functions of random variables. Okay, and that's already. Yeah, no, that's correct. That's already the really the sort of the main statement or the main idea behind Monte Carlo methods, which in principle even make them feasible. Like if you have a random variable and you have access to IID samples from it, so independent random variables that have the same distribution as x, and you compute their average, then as you take more and more, they increase the sample size, it will eventually converge to the true expectation. So this is the fundamental result of statistics somehow. It tells you, like, if you have large samples, then you can use those large samples to, well, make statements about the true unknown, like population statements. Like classically, just to give you one example, so if you would like to know what the average height of a person in Singapore or the US is, then what this result tells you? Well, actually, just collect a sufficiently large sample. So I could ask everyone in this room, not everyone in Singapore. So this is very natural that IID data appear in like statistical problems. Now, where do they appear? That's already like looking a bit into the future. Where do they appear in our goal? So what is our goal? X. So later on, we're interested in computing the value, the expectation of a function written on the stock. X is the stock. We have a function on the stock. X is the value of the stock in a year. How do I get IID data? It's a non-trivial question, so you need to generate them actually. So you will have a model, like the Black-Scholes model, that gives you the distribution, essentially, or whatever, the distribution. And you will need to use the computer to generate these IID data. So that's the difference between Monte Carlo methods and statistics, classical statistics, where IID data are not given to you, but you actually really need to take very good care, and it's not easy, as we will see, to generate them in general. Okay. So just, okay, who has already seen like law of large numbers or central limit theorem? Just that I can, okay, so maybe less than a third, okay. Okay, so I keep explaining how things works in a bit more detail. Now the next crucial statement, the second sort of fundamental statements in statistics, is the central limit theorem. This is wrong like it's written here. So this, so it would be like that, or actually the formal statement would be limit n goes to infinity square root n times Sn minus mu is distributed normal with mean 0 and variance sigma square. Yeah. So what this statement tells you is now the following. So we know that Sn converges to mu. As we increase the sample size, typical realizations of Sn will be closer and closer to mu with increasing sample size. Yeah. At the same time, so for instance, if you would say whatever mu is here, here's mu plus 1, here is mu minus 1, and say sigma is 1 just in this picture, okay. Then typically the empirical density would look for a certain n, for a certain large n, you would typically see observations here. If you run this experiment a couple of times, like I run it 10 times, I see 10 values which are here, maybe one is here, maybe one is here. So if you plot the empirical density, maybe it will look like this. Oops, sorry. So this is not. And then it's 0. Okay. But what the statement tells you is actually if you zoom in, if you have n very large, and you zoom in to, you have mu, and here you have now not mu plus 1, but mu plus 1 over square root n, mu minus 1 over square root n, and n is really large, we will need to quantify how large, then this will look closer and closer as a normal distribution. Yeah. Okay, in particular, where this result is useful is that it allows you to sort of estimate or compute confidence intervals, asymptotic confidence intervals at least. Yeah. So what it's, maybe again black, what this is telling you is that we've seen that for a Gaussian, like with 99.9%, typically it's within like 4 standard deviations, I guess, or 4.5. I don't remember exactly. Let's say 4 for the sake of it. Then that would probably, with really high probability, 99.9%, you will have mu is in the interval Sn minus sigma square over sigma, not sigma square. Sigma over square root n 4 times, Sn plus 4 sigma over square root n. This will be larger than 0.99, or 999 if you, I don't remember exactly the numbers. You can look them up in the lecture when I presented them. But it tells you that, okay, if you want to have an accuracy, like if you have some form of estimating or knowing a priori what sigma could be, then this gives you sort of the sample complexity needed to achieve an estimator, Sn, that with really, really high probability is very close to your actual quantity of interest. So what that means is, okay, maybe I should also say that. What does this probability here represent? It represents the following: 99.9%, just 99%. I run the computation 100 times. Yeah, 100 clients call me. Each time I run it, on average, 99% of these numbers will be within this very small error. There can be one which is really bad, nevertheless. But most of my numbers that I will generate that way fall inside this small interval. And n is large, n is 1,000, I don't know, 1,000,000. So it's a large number. Good. So this was I think these were the only preliminaries from statistics that we need. Now let's talk about our, sort of this is our goal, or a toy example of our goal, solving an expectation. Later on this will be not expectation in an interval, but on a high dimensional domain. But solving solving integrals. So now if for any chance we have access analytically, of course there's no error. If it belongs to the class of 10 simple functions that you can solve, like polynomials, sine, and whatnot, then you're in business. But otherwise, we've already seen actually last lecture these type of numerical solutions, like Riemann integration and trapezius or Simpsons. Maybe I'll write that down, especially Simpsons. So the idea is, of course, the following. You have a function f, that's f. You discretize, and in the standard Riemann approximation, this should be here maybe, what we did is put an equidistant grid on the domain and just take the left limits, for instance, or the right limits for every point in the spacing, and this will be our approximate integral if we just integrate this domain. And clearly, if we make it finer and finer, then if n is the number of spacings, let's call them, if you make that finer, it will be a better and better approximation. I don't know if we really showed this, but what is relatively intuitive to guess is that the total error is of order 1 over n. If I have a nice function, say the function is Lipschitz, I have a bounded domain. So this error here that I misspecify in general, that will be order 1 over n. Now, Simpsons is another rule. Just to tell you that you can, orange is not good, that you can do better actually. And this is very similar to the idea that we've seen last lecture, where we took average of implicit and explicit scheme and obtained a better rate of convergence. Yeah? By not taking just left or right limits, but same function. So what Simpsons does is I take, again, same spacing, say, I take this point, I take this point, I take this corresponds maybe to this point. And what I'm going to do is I take trapezioids. So I take this one, here I take this one, here I take this one, and you're going to end up with that's going to be your approximation of the integration. And what you can show is very similar to what we have actually shown, that this approximation of differences using differentials using finite differences, where we also had a boost in performance, that this converges at rate 1 over n squared. So it's a lot faster. And there's also other methods. There's plenty of methods, like as you can imagine. This is essential in so many subjects. So there are plenty of methods that if the function is even smoother, you have access to maybe derivatives and so forth, you can do even faster. Yeah. Now Monte Carlo will take a very different approach to this. Yeah. So these are the numerical methods, the classical numerical methods by discretization. Now stochastic integration, this has nothing to do with the stochastic integration we've seen, like Ito's integral and so forth. That's just the name here. That shares similarity. But stochastic integration uses the following idea. Remember, or keep in the back of your mind, law of large number and central limit theorem. So we want to write an integral as an expectation, and then maybe we have access to these type of methods. So what we're going to do is the following. We're going to write f as a product of a function g, a specific function g. So this function g here, times a density, phi is a density of some density that I choose, so that's my choice. And if I do that, and this density satisfies, well, two things. Obviously, it should be positive, strictly positive on the domain, and zero outside. Then I can simply rewrite the integral as an expectation. Yeah? And I mean, it's always possible. You can always choose, for instance, phi of x is just 1 over b minus a on this interval a and b. So that's the density of the uniform distribution. But at times it's it's better to keep it general because at times it's much better to take something different. Yeah? Like a normal distribution, restricted normal distribution or so. Yeah? Okay, and that was all that we needed to do to make the statistical methods applicable, actually. So now we have rewritten integral of f as expectation of this new function g. We know, okay, if we have access to IID data selected according to x, our random variable, so in the previous slide it was, for instance, the uniform distribution. If we have enough of them, then this sum of the g of xi's will eventually converge to the expectation, which was, by definition, the integral. So this is the Monte Carlo method, as simple as that. Yeah. I mean, just to give you some historical background, now the way I present it, it's relatively clear that, especially if you understand law of large numbers, that this is a trivial way of approximating these integrals. But like in the 40s, before all of this theory was rigorously developed, conceptually this is a crazy step if you come to think about it. Like I have a deterministic problem and I just throw random data at it, and that will approximate the solution. That was a very, very cool conceptual step by, I think, Neumann, and I forgot, there were 3 names. Unfortunately, when designing nuclear weapons, so that's the part of the story. Okay, now what is crucial in the next step is understanding, well, if I have n sample data, samples, and n is really, really large, then it will converge. But how fast will it converge, and what's the error that we can sort of expect on average? So that is where in our stage, where the central limit theorem will kick in. Yeah? So this is again, here's that is over n, and same for epsilon n. Yeah? So Sn is Gaussian, almost Gaussian. In fact, that is a very idealized situation. Like it can be depending on the type of problems that you have, on the data that you have. If it's a more heavy-tailed situation, it can be very far from Gaussian for moderately large n. And you really need n to be extraordinarily large for this to be truly Gaussian. But still, you can formalize similar results as here in the general situation. But that's, I mean, that would be a course more in statistics than here in quant finance. Now, and the error is again also, say, almost Gaussian with a very small variance. Like variance of your problem, variance of G divided by n. And if you haven't had any encounters with statistics, let's do this step once again. So we've actually probably almost done it, or at least done the step where we use the same principles. So if I have the sum of independent random variables, for us, I think it was increments of a Gaussian where we used it in the context of Ito isometry. But if you have sums of independent objects and we take their variance, then it's just the sum of the variances. Yeah? So we can actually write this down. So this is the 1 over n squared, because the variance is, remember, homogeneous of degree 2. So if I multiply, then I can take it out, but I have to square. So 1 over n squared. Sum I goes from 1. J goes from 1 to n. Maybe let's write this as two sums. That's better. Sum j goes from 1 to n. And now we have all the covariances. G of xi, G of xj. And xi and xj were independent. Now, if you have independent random variables and you apply any kind of function to them, what you'll get back is again independent random variables. So independent, I mean, on an intuitive level means if I know x1, it doesn't tell me anything about x2 and vice versa. Now imagine I don't observe x1, but just a part of x1, namely a function of x1, then that will even less tell me anything about x2, let alone a function of x2. Yeah? So all these sums, or summands where I is not equal to j cancel, and you'll get this form. Yeah. Okay, what's the take? I'll put this back on the large screen. What's the takeaway, what we have seen so far? I mean, if I have a closed form solution, which means that I can just calculate it, obviously there's no error. If I run any type of grid argument, like Riemann sum, or actually Simon's would be 1 over n squared. That's sort of the error that I get. And if I run Monte Carlo methods, the error that I get is 1 over square root of n. So which do you prefer? If I give you these three options, which option do you choose? This one? Yeah, I mean, if you have access to a closed form solution, you take it. Yeah. But otherwise, this one, right? Yeah, exactly. So why did I introduce Monte Carlo methods in the first place? If the error is larger, significantly larger, like this, n is like 1,000,000, then that's 1 over 1,000,000, that's 1 over 1,000. Why did I introduce these methods? there are 2 points actually. One point is, if you remember what this method, this integration method here does, is it heavily relies on the fact that the function is smooth, continuous, I mean actually smooth. Yeah? If you have a function that looks like this, it heavily oscillates. You take a grid, maybe you always catch the points where the function is at its maximum. I mean, so in the order, implicitly, you use heavily regularity of this function f. Yeah? Say that the derivative, it has a bounded derivative. Yeah? And if you think about Monte Carlo methods, so we didn't use anything. It was just that it has a finite variance, and the variance doesn't really change if it oscillates. A function oscillates more or is equally spread. It really doesn't matter, actually. So whenever, for instance, the function is bounded by a constant, you'll get a variance, of course, that is bounded. So remember, variance was just this term here. So if, say, function is in between 0 and 1, so this here is in between 0 and 1, then expectation obviously is in between 0 and 1 as well. So this here is in between 0 and 1, so the variance is in between 0 and 1. So variance is not a measure of smoothness of the function. That's the point I want to make. Yeah? And Monte Carlo methods, they work for discontinuous functions g or f, vice versa, without any. I mean, there's nothing you need to take care of. Yeah? That's one point why Monte Carlo methods, or where they're preferable. The other point is when it comes to high-dimensional integration, and that is really the true, like the true nature of, or the true reason why Monte Carlo's methods are so popular and used. Now, to make this point clear, also because I told you previously that the same thing happens for our PDEs, is that think about the following. I give you a nice function. F is a smooth function. Yeah? And I'll ask you to integrate using your favorite deterministic method on R, say, on 0, 1. This is 1. So if you want to have an error of, say, order 1 over n, 10%, yeah, what you need to do is, if you take, just for simplicity, take this Riemann approximation, you need to divide this interval into roughly 10 pieces. Yeah? And then you run a Riemann approximation. So 1 dimension, error is 10%. I need 10 spacings, equidistant. Now I ask the same question in dimension 2. I don't know why I always mix 0 and 1 here. 0, 1. In dimension 2. Okay. What is sort of the number of spacings that you need to have any chance of approximating this function? Yeah, I need to take a grid. That is relatively fine. So that is very close to what we've done in the previous lecture, where one index was time, one index was space, one variable. So in dimension 1, you need, say, 10 spacings. In dimension 2, you need 100, 10 times 10. You have 100 of these cubics. Dimension 3, you see where this is going, right? Dimension 3 is 1,000. I mean here as well, right? So you have 1,000 cubes, and in general dimension D, you need at least 10 to the D spacings to achieve an error of 10%, say. And if you come to think about what this number is, like, I don't know if this is clear to every one of you, but like 10 to the D is an astronomical number if the dimension is not 2 or 3, but say 10. 10 to the 10 is, what, 10 billion, I guess? 10 to the 20 in 20 dimensions. Yeah, if you later apply this to an option that depends on 20 different stocks, that's close to the atoms, probably, of a larger country. So it's an astronomical, really astronomical number. So that is why I said these classical methods are simply, they intrinsically cannot handle large dimensional integration. Yeah, that's just a problem. There's no way how you could avoid that in general. And if you remember, our PDE method used exactly the same idea. I discretize locally if I want to discretize and compute it, not integrals, but approximated gradients by computing gradients on the grid. But I still, again, if I increase the dimension, I need a grid, and that grid grows exponentially with the underlying dimension. Okay, so now how does this look like? So okay, I have a function f now. It depends on, this is the notation, simply like integral over r, f of x1, xd, 1 omega x1, xd over dx1 and so forth. And Monte Carlo methods, nothing changes. They will still perform with the exact same rate of convergence. Yeah. So yeah, this is here. Grid methods drastically decrease. I mean, this is useless. This is essentially constant. If you do Monte Carlo methods, exactly the same arguments that I gave before. You have a density. Now density depends on a couple of coordinates. You can think of a Gaussian if you want, where Gaussian RD is just D independent Gaussians. So phi would be just the density of a Gaussian, for instance. You define this function G as the rate quotient. Integral of f is the same as expectation of G. You simulate IID data from X, compute the empirical sum, and and exactly the same thing. So it will be a normal distribution. Here, f is, of course, it has one dimension. So f is a function that takes a d-dimensional vector and maps it to a number. Like the price is a number. And yeah, so everything that we've done so far applies. Functions of random vectors or random variables. Independent if the vectors are independent. I get the variance, that the variance is now the variance of this function g divided by n. In particular, the average error that I expect is of order 1 over square root n. Of course, the variance might increase with dimension. That can actually happen, but typically at most linearly in the dimension. And in various applications, actually it's constant. Like again, if you have a function that is bounded, say on the hypercube, you integrate a bounded function, it will again give you a variance that is between also 0 and 1 if the function was in 0, 1. Now this is the property where why Monte Carlo methods are used. You see, it's a dimension-independent rate of convergence, which is very surprising. Like if I'd asked you beforehand, at the very beginning of this lecture, give me a method that integrates a d-dimensional function where with like very few points, probably the people that have seen Monte Carlo methods would give me an answer, but I would be surprised if the majority of you would come up with this idea. Like I wouldn't probably. Okay, so this is the summary. This is the summary. Well, okay, if you have a closed form, then I mean there's no error. In a low-dimensional, you of course can prefer this one if your function is smooth or has a bounded derivative. But otherwise, the dimension is here. But otherwise, of course, Monte Carlo method is the way to go. Now, what is left is to explain how to get access to these random data. Yeah? So remember here, in both in one dimension and in d dimension, the input that we must give this simple algorithm is IID data. And what we will do next, I think we will start before the break actually, is I'll tell you how to generate those data. And just as a start, I will explain one-dimensional case. So if X is one-dimensional, and later on I will briefly touch, I mean actually not briefly, I will talk about two methods to generate random data in general dimensions. But just as a preview is that if you think about, for instance, X being the standard Gaussian or the uniform distribution or things like this, and of course you can take the Gaussian here in this method. A Gaussian in d dimensions is just d-independent Gaussians. So if you think about computational complexity, it means that if you can generate at whatever cost a one-dimensional random variable, then it means you can generate d times that cost a d-dimensional Gaussian. So it means if you must generate n data in d dimension, in this Gaussian case, what you will get is just n times d. So it's still very manageable. Even if dimension is large, it just enters linearly. Like even if dimension 100, you need 100 times more samples. But the samples are usually always in millions or at least high thousands that you use. Okay, any questions so far? I think. Okay. This is just a recap. So what Monte Carlo methods, what do they do? This is exactly what we said. Like you generate random data, compute empirical average. You have the theory that tells you, you have the theory that tells you what the expected error should be like, square root standard deviation divided by square root n. Now in practice, that's maybe one important comment here. Like in practice, you would often be interested in providing not just the number, the number your algorithm gives, but also a confidence level. So instead of telling you just the number is 100, I'll tell you the number is 100, and I know with relatively high probability that it's in between 100, that the variance has some certain value. Hence, the confidence level is standard deviation by square root n, the number that. Yeah. And in practice, of course, you don't know sigma. Sometimes there is an a priori way of estimating sigma, like problem-specific way. But otherwise, what you do is you replace sigma by the estimator for sigma. So that would be your empirical variance. And you use that empirical variance to calculate confidence, empirical confidence levels. Okay, so I feel as if today even less people are paying too much attention than usual. So what we could do is either the following. We make a break now, and 10 minutes, in 10 or 15 minutes, we resume with the methods how to generate random numbers. I'm assuming that is because some of you already are familiar with this type of stuff. But I guess what comes next will probably be new. Maybe not the first slide, but afterwards it will be new. So I propose to take the cut here, and after the break, we'll be a bit more active and start with a bit more new stuff for everyone. Okay? So 15 minutes break until 9, 10. Right? 8:10. 8:10. 8:10. Okay. 15 minutes. Yeah. Okay. Okay, let's resume. Maybe because I was asked this in the break to make well, not fair, but that everyone knows. So the midterm, I'm still in the process of administering it, but it will be in week when we have the 7th lecture. So this week, then there will be next week where you have a break. No one's going to ask anything from you. And then the week after that, we will have week 7. Yeah? And there will be a midterm. Midterm, the format will be as follows. It starts Monday morning, ends Sunday evening. You will have 60 minutes. It's online, multiple choice. You can do it anytime, anywhere you want. At whatever time you like, you start it once. You can only start it once. But you will have 60 minutes, and the questions will, I mean, as you can think, if it's going to be a multiple choice question, you will not be asked to prove anything. That will be hard. It will be more under, like, testing basic understanding of this course. So you should be fine. Like, prepare, read the lecture notes, and yeah. But you will be fine if you understand. For instance, a question here could be, when do you use Monte Carlo methods generally? And you have 4 answers. Yeah? Maybe not every question will be as simple, or maybe some questions will ask for economic reasoning, but those is sort of the ballpark of where the questions are aimed at. Or the most of the questions, at least. Okay, so wrong direction. So now what we're going to do now. So Monte Carlo methods, again, so you compute this empirical sum. It will convert to the true value. You have a normal approximation. You have confidence intervals. What is missing so far is how to generate these random data. That will be the second part of today's lecture. And we're going to start 1 slide, or 1.5 slides will be simple. And then I'm pretty confident that you didn't, or the majority of you at least, didn't see the other methods that we will discuss. Yeah? Right. So the very first thing to note is that we will essentially always use like pseudo-random numbers in this course. So Python has packages, yeah, random rand, that creates you uniform random variables. Normal, well, you can take a guess. And those numbers, you view them as really random numbers, even though if you want to dive into details, those are pseudo-random numbers generated by some clever algorithms. Like, I don't know, think of computing pi increasingly more accurate, and then rounding some indices and so forth. Yeah? But think of those as really being random numbers. The first question that we ask is, again in 1 dimension, how to get from, well, these 2 types of random variables, in particular this uniform random variable, to a more general random variable that we're interested in sampling. Yeah? Our stock price doesn't have uniform distribution. Our stock price has, say, log normal distribution. Okay, log normal I can transform easily from normal, but there's plenty of other interesting distributions in finance as well. So you need to sample from an arbitrary, in this first step, 1-dimensional random vector. And what turns out is this is actually extremely simple. You just invert, that's this cumulative distribution function. So it's increasing, maps R to 0, 1. You invert it, and you get back new random numbers. And these random numbers happen to have the wanted distribution function. Yeah? So extremely simple. Why does it work? Well, I mean, maybe we can Maybe we can do it here. So if you think about what is the distribution that if x is smaller than t, or xi is smaller than t, by definition that's the probability that phi minus 1 of ui is smaller than t. Okay. Now you simply apply phi to both sides. The probability that ui is smaller than phi, that's phi of t, and that's the uniform distribution on 0, 1, so that's just phi of t. So it's really just the definition almost, and this one step of applying phi to both sides, noting that phi and phi inverse cancel each other if you apply them successively. And that the uniform distribution, that's the defining property of the uniform distribution. Is that clear? Like, I mean, uniform distribution 0, 1, that's the density. So phi is just 1, and then phi, the CDF, you integrate this constant function, it's 1. Yeah. Now, everyone, I think that should be clear. What you can also, like, I mean, what I assumed here implicitly is that this inverse exists, right? And inverse of distribution function doesn't need to exist in general. Like if I, for instance, ask you how to generate, you have random numbers of uniform random numbers, and I'll ask you generate independent random numbers from a dice, like 1, 2, 3, 4, 5, 6. How do you going to do that? It turns out, I mean, invertibility here is not important at all. And let me actually write this down. So say do you have, I'm going to do a dice with just three sides to make my life simple. So 1, 2, and 3, okay? And it's a fair dice, say every side has equal probability. So how does the distribution function look like? So that's R, that's T, that's 0, and here is 1. How does the distribution function look like? It's going to stay 0 for a long time. The probability that I see anything below 1 is 0. Then it's going to jump up to 1. It's going to stay here until it almost reaches 1. Then it's going to stay here and jump. From there on, it will be constant to 1. Yeah. Maybe. So that's the distribution function of this three-sided dice. Yeah. And if I want to invert this function, it's clearly not possible. Yeah? But what I can still do is what is called right inverse. So that's F. I always call them F. Sorry. Phi, so this is phi. Phi inverse of 1 is defined as the smallest number, t, such that phi of t is larger than u. Yeah? So this is, I mean, always used in probability and statistics. So that's called the right inverse. There's also left inverse. It's not really important. It's the same thing, but just we just stick to this one. And this right inverse always exists. Yeah? And if you calculate it in this example, so here is 0, 0, 1, and that is sort of t, that is u. So here you had u here. It's not difficult, but very confusing, so I'll also always make mistakes when calculating this. So if you compute phi inverse at 0, then it's going to be minus infinity, because every phi of any value is larger than 0. So it's going to start at minus infinity. Minus infinity. Now, if you want a value for phi that is larger than u, where u is some small number, it will immediately jump to 0 until it reaches the value 1/3, 2/3. Yeah. At 1/3, it will jump to 1. And at 2/3, it will jump to 2. Yeah. So this is the inverse of this non-invertible function. Yeah, and I mean, the way you calculate these is, remember, so what does it say? Let's pick the value u is 1/4. So I'm here at this level, and I need to search for the smallest t for which the function is above this level. So I essentially put a piece of paper and move it vertically from bottom to the top. So here I will see this one will be the smallest value for which I achieve greater or equal than 1/4. Until here it will always be this value, and once I'm here, or anywhere here, it will jump to this value. And that's exactly what this picture does. Yeah? Now, that's the definition of this inverse, and if you just look at this picture, yeah, I mean, the calculation that we've done before can be made also with this non-invertible function. But if you just look at this picture and see, let's throw a uniform vector here, many uniform vectors. Then typically I will see on 1/3 of those, I will see the value 0. So f minus 1 will be mapped to a 0, on 1/3 of those to 1, and 1/3 of those to 3. So I get back exactly this distribution that I wanted. Yeah? If I apply the uniform distribution, the inverse of this left inverse to the uniform distribution. Yeah. Okay, and obviously that works with any discrete distribution, so not the three-sided fair dice. Okay, so this slide formalizes this once again. So what you do is you sample, if you want to sample from an arbitrary CDF, you sample from uniform, compute the inverse, apply this sample to it, and you get back a sample from the distribution that you were interested in sampling from. This works for discrete random variables as well, as we've seen, at least in this example. But what's the downside of this method, other than being one-dimensional? It's that you need to compute the inverse. And we have seen, even for the normal, standard normal distribution, you cannot analytically compute the inverse. Yeah? So of course, what you need to resort to is approximation arguments. You can tightly approximate the normal distribution inverse or normal distribution CDF. But at the same time, like if the distribution is complicated and there's no clear analytic way of tightly approximating or actually computing distribution, then that's difficult. Maybe just a side remark, because I was commented in the lecture. So here in this course, as I said, we will always use these pseudo-random numbers, but there's actually also ways to actually getting random numbers. Those you cannot create. You need to sample from high entropy observatives. But you would also, I mean, you would only do that. That's very expensive, very tedious. You need to buy these data, these really random data. But you would really only do this if you have an extremely sensitive problem. Yeah? Think about you're dealing with really classified data. You run your algorithm. You don't want, I mean, you need to be sure that either it cannot be backtracked what you were doing actually, and then you would use these type of methods. Yeah? But for us, I mean, just because I remembered, but for us, we will always use these. Have granted the uniform or Gaussian random variables as given, and we've seen here how to generate from a distribution. Okay, side quest. But right, problem was how if the CDF is complicated, I need to invert it. That's numerically very expensive. So hence, there are several other algorithms that work without inverting the distribution. Yeah? So that's what we're after now. We know how to do it in principle, but inverting the distribution function, CDF, the cumulative distribution function, is expensive. And one class of such algorithms or methods are called acceptance rejection-based methods. Okay. So this is arguably the simplest of these methods. We will see one more complicated later on in the d-dimensional case. But this is still one-dimensional. You have a density now. For instance, this exponential density that will... Actually, you will see that later on in this course when you're modeling like company default times. Then a typical model for these default or waiting times is such exponential distributions. But in general, you have a density, whatever form, not this one. And what you do is, instead of generating one random variable, you generate two uniform random variables and throw some of them away. With the following algorithm, and I will maybe explain it and then show the next slide that will give you an intuition why it works. So first coordinate is y, second coordinate is y2, and you accept y1 only if this condition is satisfied. So y2 is smaller than the density at y1. Okay? And here's the picture. So what you do is you have a density, and now comes in one engineering step. Yeah? Exponential density is a density on R plus, so on the positive free line. There's no uniform distribution on R, obviously. Yeah? So the first thing that you need to do is exactly the same thing that we've always done in our discretization methods, is sort of fix boundaries. Yeah? In this case, you would, well, according to this picture, this would be your boundary, 1.25. So you pick the boundary. Maybe I'll show it actually in a second. I'll draw the picture. That's maybe easier. Yeah. So let's do the engineering together for a different density. So say that this is your density that you want to sample from. Then you do two things. Sorry. Like this. Okay. You do two things. First of all, and it's strictly positive. Sorry. I mean, drawing here is not as easy as it looks. I mean, it doesn't look easy. I don't know. Okay, you do two things. So first, you cut off at a certain level, and you cut off so that whatever comes here has a tiny probability. Yeah. So the tiny. And we've seen for the normal distributions or any exponential distributions, you go a few standard deviations outside of the typical region, and that will be extremely small. Yeah? So tiny is like 0.01 maybe. Yeah? Now then the next step, you compute the maximum height of the density. Yeah? Whatever this is in this picture. And here you get this area where you now sample uniformly on this rectangle. Yeah? So you get 1 point here, maybe 1 point here, 1 point here, 1 point here, 1 point here, 1 point here. So you've generated those, 6 samples. In practice, not 6, but 60,000 or so. But you generate those 6 samples, and then you decide which ones to keep and which ones not to keep. So this one you will keep. This one you will throw away. This one you will throw away. This one you will throw away. Actually, all of those, except this one point, you will throw away. Yeah? You see you need a lot of samples, not 6. Yeah? And if you do this, if you do this as is here with many, many samples, then you will see what actually happens is, well, in regions where the density is high, you will accept many samples. In the regions where the density is low, you will accept very, very few samples. So all of these samples are gone. Yeah? And if you do that empirically, like in this, this is an empirical proof that with more and more samples, you will see actually a density or an empirical density will approximate the true density. Mathematically, this is actually also relatively easy to see. I mean, the samples approximate a uniform distribution. So, well, you exactly get the area in the limit of below the density. Yeah? Now, this method is super general. I only know a density. I need to have queries to the density, no inversion of distribution function, no actual knowledge of distribution function. Often the density is a much more natural object than the integrated density. And here I only need the density. So this is a very, very, very general algorithm. The price that you pay for this generality, as you can imagine, or as you can see, not imagine, is that actually many, many of these samples you produce will be thrown away. And that gets more and more severe if the density is small at certain places. Yeah. So that is the downside of this method. But it's very cool. You've seen you can now generate any density, random variable with an arbitrary density that you want, based on this as simple as you can be algorithm. Okay, this concludes one-dimensional sampling. Later on, we will see another algorithm, Metropolis-Hastings, which also in principle applies to one dimensions and it's used there, but we will put it in the framework of multi-dimensions, where it really where this one here doesn't work to this extent. Okay, any questions? Okay, now it gets conceptually a bit more, probably a bit more, yeah, you need to think a bit. So what we're going to do now is generate multi-dimensional random vectors. Yeah? And, oops, this one here. So all of what we've done so far is clearly just one-dimensional. If we have a CDF, then it maps RD to R, and intuitively I can only invert a function if the domain dimension and the range dimension is the same. That makes sense, no? So I cannot invert a distribution function. I will actually also not be able to do this pseudo-inverse because I really have many points that will give the same value. And I told you before, like if you are interested in plain standard Gaussian, for instance, where each coordinate of the vector is independent, that's the definition of the standard Gaussian, then you can just generate D independent Gaussians, put them in a vector, and what you have is one sample of a Gaussian vector. Yeah? That's trivial. But at the same time, like if you think about applications, your applications of interest in finance, then what does this X or these random vectors represent? These represent the future values of stocks, actually plural. So what you can think of to maybe make this very concrete, for instance, X could be Apple, Google, Exxon, 3 stocks. And the list could be longer, of course. Now, are those really independent? Even if you think that all of these are Gaussian, they're certainly not independent. Apple goes up, that Google will go like significantly, then that Google will likely follow. So they're heavily correlated. For instance, the first two. The third one maybe not as much. And so, oops. If you've never done this in this course so far, but like it's very conceptually, I think it makes a lot of sense. If you calculate or do models in multiple dimensions, you of course need to specify the correlation between the different variables. So it's sometimes called rho or sigma. So this would be the covariance, the correlation, and that's the matrix describing the at least linear dependence of their input. So for instance, in this example, and let's make this very concrete, how would this correlation matrix, for instance, look like? What do you think? Okay, so 1, of course, correlation with itself is 1. So in the diagonal, there will always be 1. Apple and Google are highly linear, positively correlated, so it may be 0.8. Yeah. It's symmetric, of course, because like correlation is linear. I mean, the correlation with impact of Apple on Google is the same as Google on Apple. I mean, maybe that's not the correct explanation, but yeah. Correlate is symmetric, of course, by definition. And maybe here I get something smaller, like 0.2, 0.1, I don't know. So these are just now numbers that I not real numbers, just some numbers which could be potentially realistic. So now you want to generate a random vector. that satisfies this correlation. So what does it mean? Yeah. Maybe let's make this even more transparent. So maybe let's put here 9. Okay. So what does it mean? How should your vector look like if you just check for it? So if the first coordinate of the vector is very high, like unusually high, then on most of the samples, for those such samples, most of the samples, the second coordinate should have the same atypical behavior, the same tendency. Yeah? So if it doesn't, then something is wrong with your simulation, with your model. And so how do you generate those data? Is by generating independent Gaussian data. So these are independent. So that's again, Z is a vector, yeah? So Z is Z1, Z2, all the way to ZD. You have a vector of independent Gaussians, and you apply a linear transformation to it. Intuitively, I mean, you can model correlation. We'll come to that in a sec, at the end of today's lecture. So let's keep it like this now. So what is the linear transformer that you pick? It's any type of square root of this matrix, covariance matrix, actually not correlation matrix, covariance matrix, covariance matrix. And what you typically do numerically is you take the Cholesky decomposition. Yeah? Now, okay, so what you take is any matrix that satisfies that. And there are plenty of those matrices, or some matrices. I mean, you can think of, like, if you take, what is this actually? Like, it's the analog to the square root. If this would be one-dimensional, M would be just the square root of rho. And even in one dimension, like if you take 4 and the root of 4 is, well, 2 or minus 2, both is fine. Yeah? So minus 2 times minus 2 will also be 4. So there are various notions of roots. And one of those is the Cholesky decomposition. So this one is a lower triangular matrix. So M is something, 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 something. And here always you have 0. So it's lower triagonal. And the reason you typically prefer Cholesky decomposition is simply because if you just take, for instance, really the standard root, it's not numerically stable. Cholesky is significantly more stable numerically. Yeah? Like taking the root, like intuitively you can think of this as taking inverses to some extent. And that is just, for matrices, that is just not a simple task. There's formulas, but I mean, I don't know if you've ever, by hand, calculated inverses of matrices. This is horrible. Yeah? So it's not an easy problem, not for you, not for the computer. So that's why you choose this Cholesky decomposition to make it slightly more stable. Okay, and if you do that, then that's sort of the calculation that tells you the correlation or the covariance of X is exactly what you aim for. Okay. I mean, if you're not familiar with matrix calculation, I mean, this is really just the rules of linear algebra. Transposed, multiplication and transpose, they are commutative, not commutative, but with this you need to change the order, and expectation is linear, you take m out, and so forth. You can also do this one, I mean, you can just also write down what you actually have here. So x dot x transposed at I, j, or maybe let's call them A and B, is just m a mx a. Is that correct? No, I'm confused. Okay, maybe let's maybe let's keep that as an exercise. Yeah. Okay, but it's not difficult. Okay, but that's how you generate d-dimensional random vectors that still follow a distribution that is very simple, so to speak. So a Gaussian distribution, for instance, with a different correlation or covariance structure. But still, what it requires is that, well, if you've put it in this form where you have zero correlation, that all the random variables of z are truly independent. And now if you've studied some statistics or math, then you know that independence and uncorrelated are two different things. Like random variables can be uncorrelated, but heavily dependent. Yeah. Yeah. So this is this method here. Well, as a first start, it generates data with prescribed covariance, but not necessarily all types of data. What is a very, very powerful and popular algorithm is the Metropolis-Hastings algorithm. Yeah. And okay, sorry. Before the Metropolis-Hastings, just the summary of this Gaussian multivariate sampling. And of course, like this applies to log normal, because log normal is just a function of a Gaussian. So for us in this context of this course, you actually already get quite a lot of like Black-Scholes framework type problems you can sample now. Simply by sampling independently the standard Gaussian random variables, one-dimensional, computing the transform, and, well, computing g of xi in the standard Monte Carlo method. Yes, so high-dimensional sampling. This is 1, not 2. Not sure if that's interesting. So this method is, we will not see the proof, but this method is extremely popular in machine learning or variants of these methods. The reason, or the framework is the following. You have a density, which typically is called pi. Previously it was called phi, but let's call it pi now to be consistent with the standard literature. And this algorithm is different to the algorithms that we've seen so far. Yeah? So what it does, very similar in some sense to all our recursive dynamic programming methods, or to the PDE method where we started and computed the next row and then the next row. You do the same thing here. You initialize with some x0. Yeah? So t is 0, that's sort of the initial step. And then you proceed to compute the next step. And you compute the next step as follows. You have a proposal distribution that is, for instance, just a Gaussian, centered at your current step. So here I am at the current step. I generate a Gaussian that, say, proposes a step to the left or to the right of a certain magnitude. Yeah. I sample, this is the next proposed step, and I again accept or reject But now what I'm going to do is I accept with a certain probability. Yeah? I accept if this quotient is high. So this is a mistake. So here instead of this fraction you have pi of yt plus 1. And here you have pi of xt. Yeah? So what does it mean intuitively? And I'm not going to be able to, I can later on say how these type of results are proven. But just to give you an intuition, yeah, very broadly, you sample from a density. Think of the density as it is very large somewhere and very small somewhere. Then what you typically expect is a lot of samples in the region where the density is high. Yeah? Higher density means higher frequency of samples. So if the proposed step that has a high density, higher than the state where you are, yeah, so pi of proposed step is the density of the proposed step. That's a very large number compared to where I am at this moment. Then this fraction is large, then that means alpha is large. So means if alpha is 1, I'm certainly going to accept. Yeah? So I'm increasing the probability at which I accept this proposed step depending on the ratio of the densities. Whereas, on the other hand, if I propose a step or this proposes a step where the density is very low, I know I shouldn't see samples there. Yeah? That means alpha is very small. That means I will reject. I will just stay here where I am. Yeah? So and the reason that the cool or interesting thing is that you do this accept-reject step at random. Yeah? So you don't accept simply if pi, the next step, proposed step, has a higher density than your previous step, because what would happen then? You would just run into the maximum of the density. Yeah? If you just accept steps where the density is higher, eventually you run it for a long time, you end up at the maximum of the density, the point which is maximized. Now what this does is sort of keeping a balance between maximizing density and at the same time exploring all the space. Yeah? And what you can show now is the following. So these samples, xt, are not IID. It's, yeah, I mean, with certain probability, I'm just going to stay where I am, so it cannot be IID. But nevertheless, they behave very, very similar to IID data. For instance, this Monte Carlo framework continues to hold for these data. I have a law of large numbers. And I also have more theory to it, but stating that is very complicated, so I'm not going to do it. Right. So this is a very cool subject. This gives you a very cool result. You just plug in the density. The algorithm is again extremely simple. What I do is I just generate Gaussian data, for instance. Yeah? Proposal distribution is just my current state plus a random Gaussian. That's it. So it's a very simple algorithm. It converges actually pretty fast. So there's a sort of burn-in period. So you need to run it in practice like 10,000 steps maybe, typically, where this will do nonsense. But after that, it starts to really behave like IID samples. And pretty fast. Yeah. So the math theory, if you're interested in just 2 words, this is based on like ergodicity of Markov processes. So these are Markov processes. And Markov processes have a certain ergodic behavior if they're, well, satisfy proper assumptions, which this algorithm, if you choose proposal distribution and so forth properly, satisfies these like reversibility and so forth assumptions. Okay, and this is also, by the way, the algorithm or these type of algorithms that are used in all kinds of Bayesian machine learning algorithms, where you have priors, very, very complicated functions pi. Yeah. Okay, maybe that I will not go into more details here. Okay, so at this point, we almost know everything that I wanted to tell you today. We know how Monte Carlo works. We know how to control errors of this random algorithm. We know how to generate various ways how to generate data depending on the structure of these data. There are three unfortunately, that I want to still discuss. The first thing is variance reduction. And variance reduction, so you don't need to understand these. I will go through them also a bit quicker maybe. You don't need to understand the full scope of this, but it's important that you at least know the existence of these methods, because you will hear it when talking about Monte Carlo methods. Yeah, so you need to at least understand, well, the very, very basics of it. And the variance reduction, the core idea, where this starts is here at the following. When we compute the empirical sum, we can compute the empirical variance. And if I truly have IID data, then that's an equality. That's the empirical variance. That's the variance of this empirical sum. Yeah. And remember, what we used is, to do this, actually, this is the true formula is different. The true formula here, there was a step where we take covariances over all pairs I and j. Okay? And we use that, well, if you're uncorrelated or independent, then the covariance is 0. And all these covariance terms actually cancel. Now, but what if you could generate data for which this covariance of the g's is negative? So where this term here, okay, you have g here as well, g is missing. But where this term here, that previous was 0, is actually negative. Then it means that, well, the variance of this Sn, epsilon n, actually will be much smaller than this term. Yeah? This term will subtract. They will not just cancel. They will add some negative value. They will subtract. And that is the idea of variance reduction. One idea of variance reduction, actually. Yeah? Yeah, so that's what I said. Yeah? So this is the true form of the variance. And now you can think, now it becomes problem specific. So now you need to know something about G in order to make this work, because in general, I mean, there's no reason why you should be able to generate data for which G of the data is negatively correlated. Yeah? But one example, to give you one example where this works. Yeah? So say that it's like this. So this is my function. And I'll generate a data point and say that the data point is here. Then instead of generating a new data point, what I will do is I will, so that's x1. I will mirror x1 and introduce the next sample, which is just mirrored at some axis at some point. Now, what happens if the crucial part here is G is monotone? Yeah? So what happens? Why are these random variables uncorrelated, negatively correlated? Exactly, exactly. So if x1, say, were to increase, yeah, so x1 goes, increase means here in the, let's say, decrease, so moves further to your left, yeah, then g increases, g of x1 decreases, but g of x1 tilde, which now by definition increases. So they're negatively correlated. Okay? Crucially, of course, in this method is that g is increasing. If g is, or monotone, it could be also decreasing. But if g is convex, for instance, that of course doesn't work. And you will also see that also, like if you run it, it will not converge even. You will get nonsense for convex functions, for instance. But if g is monotone, it works. And yeah, I mean, here what you do is you take first sample, half of the sample, or just generate until n over 2, mirror the sample, you get something with smaller variance. But the function, in each of these methods, the function needs to satisfy something. You need to know something more about the problem. At the same time, like many functions that you're interested in finance do exhibit some sort of monotonicity. Price goes up, payoff should go up. Like, yeah. So that's a valid approach. Okay, next is actually a very simple idea that at the same time still is quite useful, which goes under the name control variables. And I mean, what it does is, let's take it to the extreme first, and then you'll see immediately. So let's say that actually you know already the expectation of g. Then you don't need to sample. I mean, you just know it analytically. Yeah. And what this method does is say, well, I don't know g, of course. That's what I want to compute. But say I know the expectation or the price of an option which looks very similar, has a very similar structure. Very similar here means that the variance, the covariance of g and c is small. So what you then just do is, I mean, that's sort of an approximation in L2 actually. So what you do then is you just add beta as a tuning parameter. You take a tuning parameter and you add to each of the g of xi's the c of xi minus the true expectation of c, which you know, that's the assumption. And g and x are exactly not independent, so the covariance, that's what you're aiming for, finding c where you have strong dependence. So the variance is then just given by these three terms. So variance of the sum of two things is just variances of the individual ones plus covariance. Is that clear? Okay, for those who are listening, it appears to be clear. And now you can optimize further over beta, the tuning parameter. So you can calculate first order conditions. It's a quadratic function. You minimize over the quadratic function. You get the exact form of the minimizer. And if you plug this in again under, if you plug this in in the global variance, then what you will see is, okay, sigma squared, that was the variance of G that we were given, times something that is smaller than 1 in general. Yeah? And the higher this correlation, so that is the correlation or covariance, I don't know, of G and C, probably correlation. The higher the number or the closer to 1, well, the smaller the variance to expect. So yeah, simple method, again, still quite useful. Often you have options that look kind of similar, not exactly, but kind of similar, have similar structure. Use them as a proxy. You improve immediately, for free, improve your results, your accuracy. Okay. Two further topics. Quasi-random numbers is a topic I generally really don't like, but we have to do it. And then one slide about principal component analysis after this one, and then we're done. Yeah? I think. I hope. Yeah, I think so. Quasi-random numbers are being sold as like using the same principles as Monte Carlo, but considering very accurately like good random numbers, which are deterministic numbers. And the results that you see are as follows. So quasi carefully selected variants that are not random. At the same time, the error, so the Monte Carlo error is 1/√n. Quasi-random numbers have error rate 1/n. But this logarithmic factor, and at first logarithmic factors, I mean, I probably told you at some point, ignore logarithmic factors. They're constant almost for the sample size or for our problems. But it's multiplied by d. Not multiplied. It's d is in the exponential. Yeah? So even like what is log of, say you have 1,000 samples, log of 1,000 is order 10 maybe. So you still have 10 to the d as a, not in the rate, but you still have maybe 10 to the d divided by n for large n. Yeah? So which means that these methods, even though they are heavily used, have not really a theoretical background to justify why they work. Like, okay, of course, in 1 or 2 dimensions it's fine, but as the dimension is really large, there's no guarantee, and like there's a huge theory to practice gap. Yeah? Theory says they don't really work. The worst case error is very bad, but in practice you will not see this worst case error. You will actually, the results that they give are usually quite surprisingly good. Yeah. So how do they work as well? In 1 dimension, it's really just Riemann integration. Let's go through this quickly. So 1 dimension is just evenly spread spacings, points. So it's exactly the Riemann integral. In higher dimensions, it's more complicated to generate these points. There's like that would take us a bit too far, but like in high dimensions, like where really dimension is 20, 30, distributions start to, in some sense, degenerate. So a high dimensional distribution of a Gaussian looks very, very different than what you would expect. Yeah? And they use these type of the degeneracy of high dimensional distributions. Oops. What is that? But yeah, so those are then called low discrepancy sequences. Yeah? These non-random perfect points. and you use them to calculate the Monte Carlo to average. Okay. Okay, let's do this one. And that's the last slide for today, I think. So principal component analysis is something that you should have. If you haven't heard it, then yeah, wake up, please. And that's a really important concept. And what this concept says is that very often you have problems in extremely high-dimensional spaces or high-dimensional problems. Yeah? Think of S&P 500. You have 500 different stocks, but they're not really independent. Yeah? They have a lot of dependency. And actually what typically happens is that there's few driving factors, and the rest of the problem can be almost explained through that. So let me maybe write this here. So think about a random vector which is of the following form. Yeah, x is in Rd, d is large, yeah, and maybe x1 has normal distribution 0, 1, x2 has, maybe I put them up, so x, that's x1, x2, xd. And d is 500, say. x2 has normal distribution, some u2, 1, and so forth. And x5 already has distribution something and a tiny number, 0, 0, 0, 1. And starting from x5, these numbers are, the variances are extremely small. Suppose that this is the vector that I'm giving you, the covariance structure that I'm giving you. And I'm asking you, well, compute the price of an option written on this vector. It's a 500-dimensional problem, but without thinking too much, and I tell you do it fast, then without thinking too much is what you will say, hey, maybe let's ignore all of these coordinates where the variance is extremely small. Yeah? They're not really random. They're just a number. Yeah? If I replace them by their mean, probably shouldn't matter too much. Yeah? And that's exactly what principal component analysis does. Yeah? So do all of you understand this problem in this very simple example? Okay, so exhibit the low dimensionality of the problem. That's the task we're doing, and this is used. I mean, it's hard to find statistical application where some form of PCA, this one or more complex ones, are not used, because this is just such a natural and important and powerful method. So what you do in this PCA in our context is, well, of course, this random vector is not given to you in the form that there's no correlations. Typically, there will be correlation, but nevertheless, you have the same phenomena that there's maybe a couple of them, and I will call them S coordinates, or really random independent inputs that drive the system, and the rest can be explained through them, essentially. So the way you formalize it is the following. You have this covariance matrix. I'm now writing with covariance matrices, sigma, and you put it in diagonal form. So these matrices V are just orthogonal rotations. Yeah? That's linear algebra, that it's possible. Yeah? So what it means is you change the coordinate system, and after this change of coordinate system, the covariance is in diagonal form. So exactly in the form that we had before. Like it's uncorrelated or independent even. And the eigenvalues are in decreasing order. Let's put them just there. Yeah? That's yeah. So this one is a large variance. This one is a slightly smaller variance. The last variance is the tiniest. And now what I just do is, okay, x I can write as, by definition, that is the same linear transformation as before. Yeah, where I told you like there's plenty of roots of a matrix, Koleski or this one. So x has exactly that form. Z has uncorrelated or even independent entries. And now what I do is that I define a proxy for x simply by throwing away all these coordinates or the randomness of the coordinates where there's very, very little randomness. Yeah? And this will be a proxy for S. It will again live in the full dimensional space because this rotation takes the vector wherever. So you will not see that there is this 500-dimensional vector may move a lot in every direction, but this movement is somehow inherently low-dimensional. And what typically happens now, all of that is useless if the eigenvalues would look like this. Yeah? If here you had 1, 2, well, that's 1, 2, 3, 4, 5, 6, 7, 8, whatever, yeah? D. If the eigenvalues would look like this, meaning the variance in the system of the coordinates, then this method would be really useless. Yeah? I mean, I would really throw away a lot of randomness. But what actually happens is that in many, many applications, it looks something like, that's maybe too extreme, it maybe looks like something like this. Yeah? So there's really a phase transition. Really a handful, are significant to randomness. And there's plenty and plenty and plenty that do not contribute too much. So in this example, what I would do is maybe this could be my S. S could be 4 in this example. Yeah. And of course, the larger the S, the better the approximation. But yeah, if 4 instead of 500, that's certainly an advantage. Yeah, and maybe I'm giving up some accuracy, but depending on the problem, that's what I'm willing to take it. Okay, this is all that I wanted to say. We have covered this already. We will see all of this, what I told you today, relates to pricing simply by what we will see, that prices are just expectations on a risk-neutral measure. We will do that next week. Next lecture. Next week there's no lecture. You're free to do whatever you want. Next lecture will also be the last lecture that I teach. After that, Semi will take over. And maybe what we can do if you want, there's also the midterm, but we can do a Q&A session at the end of the lecture for these fun periods of like foundations of this course. If you have any, you can ask me how, hey guys, after every lecture, but like next lecture we can maybe aim for that if you want. And that's it. Otherwise, I wish you it's too late. Yeah, happy recess week and enjoy your time.